Okay, I think we're good to go. We have a room full of visitors, and we have our speaker here ready to go. My name is Lisa Stewart, and I am Chief Administrative Officer at the Kavli Institute for Theoretical Physics in Santa Barbara. It is my honor today to welcome you to the 7th in a series of talks by NSBP's Innovate Seminar Series. And today our speaker is Morgane Konig. Close to that. I am not a French native speaker, so I tried. And this is a speaker series presented by the National Society of Black Physicists. And our speaker today comes to us from UC Davis. Today's talk will be approximately 30 minutes and presented in webinar format. This means that we will hold questions into the end. So as you have questions throughout the talk, please type them in the Q&A section, and our speaker will try to address these questions at the end as time permits. Next up, it's my pleasure to introduce you to Farah Simpson, who is the leader of NSBP Student Council, which is also the group responsible for leading this Innovate Seminar Series. Thank you again for joining us, and we hope you enjoy today's talk.
Hello, everyone. Welcome back to the NSBP Innovate Seminar Series. Thank you so much for joining us again. This seminar series is a new forum for members to share their research ideas and projects in a non-specialist way with a wide audience. As Lisa said, this is a 30-minute talk followed by 15 minutes of question and answer, and it was curated by the Student Council for our members to engage in each other's research. And we're very excited that this is our 7th talk, and we hope that you continue to join and support our series. And I would now like to introduce the President of the National Society of Black Physicists, Dr. A.Linde.
Thank you, Lisa and Farah. It's great to be here. And we're very excited about our next speaker. Morgane, soon to be Dr. Morgane Konig, hails from Paris, France. She is part of our NSBP family, an NSBP member, and she did her undergraduate studies, both undergraduate and master's degree in mathematics and physics in Paris, and then moved to UC Davis, where she's finished up her PhD dissertation under the supervision of a colleague of mine, a great cosmologist, Nemanja Kaliper. And Morgane's actually been also co-leading a group of brilliant young Black theorists, including our own Delilah Gates and others, on a weekly meeting called Nexus, where they engage and talk about do lots of calculations together. So anyway, in a nutshell, we're very excited to have Morgane tell us about her musings in cosmology. It's all yours.
Thank you for the lovely introduction, and thank you for having me. Okay, so today I'm going to tell you about inflation and a particular model of inflation called hybrid monodromy. And this is based on the work that I did with my advisor, Nemanja Kaliper, and a postdoc, James Cargill. So today I'm really going to try to motivate inflation. Why do we need inflation? And then what do we need to build a model of inflation? And then in the third part, I'm going to try to explain to you why this hybrid model of inflation solves a lot of our problem and is a good solution for inflation. Okay, first of all, what is inflation, or should we say, when is inflation? Inflation is a moment in the expansion of the universe, in the history of the universe, that lasts from 10 to the negative 36 seconds to 10 to the negative 33 seconds. And during that very short amount of time, the universe is going to expand by a factor of 10 to the 26. So at this time, the universe is very young, it's very dense, and it's going to expand extremely fast. To give you an idea, the expansion during inflation is as much as between the end of inflation up to today. So this model of inflation as an idea of expansion has been developed mainly by 3 brilliant physicists, A.Linde and A.Linde, and sorry, just a little technical issues right here. Oh, and Andreas Strominger. So, okay, first of all, why do we need inflation? Why did these physicists need to come up with this idea of an extremely fast inflation, an extremely fast expansion of the universe? And so it really came from observation. So here we're looking at the oldest map of the universe. This is called the CMB, the Cosmic Microwave Background. And this is the stage of the universe at 380,000 years after the Big Bang. So again, at this stage, the universe is still very young, but photons are free to propagate, and they propagate all the way to us. And this gives us a lot of information. So what are we looking at? We're looking at difference in temperature. So the hot spots are the red one, the blue spot or the cold one. But overall, it's extremely uniform. It's at 2.7 Kelvin with with hot spot and cold spot, they're again still very close in temperature. And the reason why this is surprising is because it's extremely uniform. To give you an example, if you have a soup and you put it in the microwave and you warm it up, your soup is not going to be the same temperature everywhere. But the microwave background, the CMB, is basically the same temperature everywhere. And so looking at that map, we can also evaluate the power spectrum, and that gives us a lot of information about the cosmology. We can get information about the density of photons, about the age of the universe, etc., etc. So we get really a lot of information. Another thing that's important about this map is that although it's extremely uniform, we don't want it to be absolutely uniform, because those cold spot and hot spot, those difference in temperature, those difference in density are the seeds for the structure that we see today. Okay, so what do we know about the universe? We know the universe is very old, 13.8 billion years old. It's very homogeneous. It's almost perfectly flat, and it's made of all the good things. It's made of galaxies, etc., etc. And it looks like it's filled with those very small structure that we see in the CMB that, again, are the seeds for the large-scale structure that we see in the universe today. And that rose a couple of questions. First of all, why is the universe so flat? Why is the universe so homogeneous? It's called the horizon problem. What are the origin of the structure? What are the seeds that are going to evolve and give us the galaxy that we see today? Or mainly the main question is, how do we reproduce those observations from arbitrary initial conditions? Okay, so let's look at some of those problems. The horizon problem. The horizon problem is the problem that, again, we have the same temperature everywhere. So if we look at those 2 points A and B, they're very far away. And what is interesting is that with the old model of this Big Bang, and if we look at the past light cone of those 2 points on the right here, it appears that those 2 points were never in causal contact. The two orange triangles never meet. There is no common area. And so those 2 points were never able to exchange information. But then if they were never able to exchange information, how come that they have the same temperature? Another way to think about it is to look at the Hubble sphere. If you're inside a Hubble sphere, if 2 points are inside a Hubble sphere, they're able to communicate, they're able to exchange information. But here, the Hubble sphere with the old model of the Big Bang, the Hubble sphere radius is extremely small. So again, those 2 points P and Q look like they were never able to exchange any type of information. So how do we explain the fact that they have the same temperature? We can also evaluate the number of causally disconnected regions that are not able to communicate. And we find that this number is 10 to the 9. We have 10 to the 9 causally disconnected regions in the CMB, but they're all at the same temperature. Okay, another problem is the flatness problem. The universe is flat, and one way to evaluate this is to look at this omega, that's the actual mass density over the critical mass density. And we know today that it's roughly 1. But in order for this to be 1 today, it would have had to be 1 to the 10 to the negative 60. It would have had to be exactly 1 earlier in the universe. And this is also something that we don't really know, we didn't really know how to explain. So now let's see how inflation solves those problems. So again, here, remember, we have that problem, those 2 points with those orange regions that were not in causal contact. But what if we're able to think about a mechanism that would push the beginning of the universe earlier in time? If we do this, then those 2 points would be able to be in causal contact earlier. Then the universe is going to expand very quickly, and they're going to get out of causal contact, but still keep some information, and hence have the same temperature. We can also express that looking at the Hubble sphere. So again, if 2 points are within the Hubble sphere, they can communicate. So if we think about a decreasing Hubble sphere from earlier in the universe all the way to the CMB, we can see that those 2 points not only were in causal contact, but this region was able to exchange information. Now to the left, you can see an expression of a decreasing Hubble sphere. D to dt AH minus 1 is the Hubble sphere. And so A is the scale factor, it tells you how the universe expands, and H is the Hubble parameter. And by doing a little bit of calculation, we realize that if we need a decreasing Hubble sphere, it's equivalent to having an accelerated expansion. A double dot is positive. And that's why when we talk about inflation, we talk about an area of accelerated expansion. Okay, so inflation, which is again, an era of accelerated expansion, solves the horizon problem. Now, does it solve the flatness problem? So we can rephrase the flatness problem looking again at this omega parameter. And remember, we need this omega parameter to be basically 1 earlier in time. And one way to, again, to solve that is to have a decreasing Hubble sphere. We need AH to be very large so that omega minus 1 will be very small. And so a decreasing Hubble sphere solves that problem. And remember, that is the same statement as saying that we need an accelerated expansion. So inflation solves both the horizon problem and the flatness problem. And inflation, to have inflation, we need a decreasing Hubble sphere, which is the same thing as saying we need an accelerated expansion. And if we want to fill the universe with a particular fluid, we need a fluid that satisfies the following set parameter, this W smaller than negative 1/3. Okay, so now how do we build a model of inflation? Because we have no preferred direction, the first thing to think about is to look at a scalar field. So this is the action of a scalar field. We have gravity, it's dynamical, we have a potential, and we can look at the equation of motion where we have a friction term, this is the term on the right, and a restoring force. So now we talk about slow roll inflation because we can define 2 parameters, epsilon and eta, and if those 2 parameters are small enough, you know that we can have inflation that lasts long enough to give us what we see today in the universe. So epsilon here is going to be a measure of how flat the potential is, and eta is going to be a measure of how long it stays flat. So we do want a potential, but we also want some quantum fluctuation because those quantum fluctuations give us the seed for the structure formation. So we do need quantum fluctuation in order to have those little difference in density that give us, again, the large structure that we see today. But if we have quantum fluctuation, this can spoil our potential. So we need to be able to control those quantum fluctuations. Okay, here we can just evaluate how dangerous those would be. So on the first, on the left part, we look at how the inflaton interacts with itself. So the inflaton is going to have to couple to other particles because at the end of inflation, the inflaton is going to oscillate and give us the particle from the standard model. So we can at first look at the self-interaction of the inflaton. But if we look at it, we realize that we get a correction in log. So those corrections are actually controlled. We can also look at how the coupling between the inflation and gravity is going to affect our theory. And those quantum corrections have been calculated. And if we make sure that the potential is flat. And if we make sure that the potential is flat for long enough, it doesn't seem to be a problem either. So again, it looks like one way to solve those issues is to have a potential that is flat and that is flat for long enough. And one way to have that is with a shift symmetry. If we have a shift symmetry, we have a flat potential. So we want it to be flat, but not forever. Okay, so we keep this idea of we want something to be flat, but let's just look at a particular model of inflation, just the easier model we can think about. We have a dynamical field, we're going to give it a mass, so that gives us this potential. Here we want to evaluate the slow roll parameter, and remember, if those parameters are small enough, we have a good theory of inflation. But in order for those parameters to be small, we need to start with a field with a value that would be above the Planck scale. The Planck scale is the scale above which we are in the quantum gravity realm. So here we need to start with a field in the quantum gravity realm, and that can be a problem because then we have to control the correction coming from quantum gravity. Okay, so again, we need the potential to be flat. We need to be flat enough. We need what we call a shift symmetry. Shift symmetry gives us a flat potential. So this is an equation that maybe is a little complicated. There's an action, we have gravity, we have a dynamical field, and we have this 4 form. But in a nutshell, we have here shift symmetry. But in a nutshell, if we look at the dynamic of this action, it just ends up being a theory of a massive scalar field with a shift symmetry. But here, if you look at the last equation at the bottom, we have this Q. Q here is a constant that we can choose. And every time we choose a constant, we jump from one possible potential to the other one. And that is why it's called monodromy. Monodromy means choosing a path. So here what we do is we are going to choose a value of Q. We're going to choose a particular path, and we're going to realize what we call a monodromy. Okay, so the model that we did, we looked at a monodromy because remember, it has a shift symmetry, which ensures that the potential is flat and it's flat enough. So once we have our model, we also need to make sure that it fits the data. We need to make sure that it gives us the cosmological parameter that we want. And one of the great things about our model is that it keeps the field sub-Planckian, that way we don't have to worry about the quantum gravity corrections. So this is the model, and instead of one field, we have two fields. We have sigma and phi. So phi here is still in Fleeton, and sigma is called the waterfall, the waterfall field. So what's going to happen is sigma is very quickly going to reach its minimum, and then we're going to effectively end up with a theory with only one field, phi. So that idea came from A.Linde, who developed, the method that is in green here. But the issue with this theory is that it did not give us a good spectral index. The spectral index tells us how our theory is scale invariant, and we know that it has to be around 0.96, but his model gave something that was greater than 1, so that did not fit the data. Now, Stewart came up with a different model. We still have the coupling. It's a little bit different. We changed the convexity of the potential, and this time we get correct cosmological parameters. But the problem, if you look at it, is that phi does not have a mass, and we do not have a symmetry, a Z2 symmetry. So we thought, okay, how can we get the best of both worlds? Well, we can just add them up together, make sure that inflation is in the Stewart regime for long enough to give us the good cosmological parameters, and that at the end, it's going to be in the Linde's regime. So again, here, even though it looks complicated, it's always the same story. We have sigma being the waterfall field that is going to reach its minimum really quickly with a certain value on the right. And then we're going to end up with an effective potential that is only going to depend on phi. Phi is going to be the only dynamical field. And then here what we had to do is make sure that we had the good values for our parameters. So our parameters here are m, big M, lambda. We need to find good parameters that would ensure that we are in the Stewart regime long enough and that we end up in the Linde's regime. So we looked at the data and we looked at three particular cosmological parameters: the spectral index that I talked about earlier, the scalar fluctuation that's around 10 to the -5, and the ratio of gravitational wave to density perturbations that also need to be small. And we were able to evaluate those values here, NS, R, and D over rho. And we were able to keep our field sub-Planckian. So here we showed that actually, although Linde's model didn't work, we were able to resuscitate that model of monodromy with two fields and to keep the field sub-Planckian, so we did not have to worry about quantum gravity corrections. We also had to make sure that our theory was stable against quantum corrections. And to do that, we perturb the background and we look at one loop effect to make sure that the mass corrections would not spoil our theory. And here in red, this is the only one that we had to worry about, but by looking at them and comparing it with the previous values for our parameters, we actually realized that that was also controlled. So, okay, now why are we worrying so much about monodromy? Why do we need two fields? So the reason why monodromy is favored is because monodromy can be derived from a string theory, from a higher dimensional theory. And so in that way, it has what we call a UV completion, or in other words, we have an argument of naturalness. This theory can be derived again from a theory with a UV completion. So here what we also had to do is we had to write this theory in a complicated form. So again, we started with a theory of two scalar, but we need to show that we can write it in terms of those four forms, because when we write it in those four forms, we have a better argument to say that it can be derived from a string theory. And we were able to do it. So now again, we have a theory of two scalar that is stable against quantum correction, that give us the correct cosmological parameters, that stays sub-Planckian, so we don't have to worry about the quantum gravity corrections. And so this is, I think, a great way to think about inflation, because again, this is a natural theory that comes from a high-dimensional string theory that has a UV completion that is stable, that gives us all that we want, that fits the data, and that is protected from quantum corrections. So now what do we need to do is that, so we realize that the dual at weak coupling, we have to do it at strong coupling. We know that it can be derived from a string theory, but we still have to really like show it, do all the mechanism. And then there's a lot of different avenues that we can think about it. At the end of inflation, what happens? The inflaton is going to oscillate. It's going to give us all the particles from the standard model. This is called reheating. So we can also see how does our model behave during reheating. And another way is here we looked at two-field inflation, but we could also look at three-field inflation, four-field inflation. What can we learn from those models? Is it more stable? Do we get better, a better mechanism? We can also look into this avenue. Why? Because again, string theory favors multi-field inflation. So this is another avenue that we could explore. All right, thank you very much.
Thank you so much, Morgane. I was very much looking forward to this talk, and you did not disappoint. We have some comments, wonderful. So if you have a question, could you just put your question in the Q&A box, and then I'll moderate questions and answers. Okay, so our first question is from the renowned cosmologist, Dr. Chanda Prescott-Weinstein. Thank you for attending. Her question is, can you say more about your definition of naturalness? Is this Hopf naturalness?
So the way I understand naturalness, maybe it's just kind of a buzzword, or it's the fact that we have a theory that is UV completed, a theory that comes from a string theory, because when you look at models of inflation, you can kind of come up with any effective field theory, look at the cosmological parameters and say, okay, this is also possible. But one way to kind of discriminate between those different models and justify the use of a particular effective field theory is to say, yes, it can be derived from a string theory. It has a UV completion. And I think that's what I mean when I talked about naturalness.
Thank you. We have time for just a few more questions. Do you have any? Or everything was so clear that everyone understands everything. Okay, so we have another question. How does axion monodromy fit within the swampland criteria?
I'm not sure what you mean by the swampland criteria. The way I understand the swampland, again, is this idea that there are a lot of different possible theories for inflation. How does this one is favored compared to the other one is, again, because the axion, this theory can be derived again from a string theory. I mean, you have axion in models of string theory. And so that way, it would be, again, natural to end up with an effective field theory that would involve an axion. I'm not sure I'm answering your question, but yeah, this is how I understood it.
Yes, if you have any follow-up questions, please feel free to put that in the chat. We have another question. If there is, oh, sorry, have you thought about preheating in this model?
No, we haven't. We haven't, and this is something that I would be very interested to explore, because I mean, as you see, we kind of put two models together. We have the Stewart regime, we have the A.Linde regime. That is going to dominate at the end, and that is at the end of inflation. Our waterfall field is not going to be in its minimum anymore, and it's going to start being dynamical. And that is, I think, extremely interesting to see how it's going to end and how it's going to give rise to the particles from the standard models. So I haven't had time to do it, but this is something that I would be very interested to do. Yes, yes.
So I actually want to make a quick comment. Can you hear me?
Yeah.
Yes, we can hear you.
Yeah. Actually, Professor Weinstein's question is on point, right on point. So in the context where this axion field in this axion monodromy model, just to focus on the axion field alone, corresponds to a global U1 Pechi-Quinn symmetry. It is exactly what she meant by a tough naturalist. So in that sense, the global symmetry is restored exactly. And so naturalist is exactly in the sense that Professor Weinstein meant it. So thanks for that question. Just want to clarify.
Yeah, thank you.
Thank you, Dr. Alexander. And our last question that we have, are we closer to proving string theory's existence?
That's a good question, because again, I remember when I started grad school and I thought, how can we prove string theory? Because you have to be at an energy that is so strong. But this would actually be an avenue to do it if we're able to show that one of this effective field theory that comes from a string theory is the correct one. Then it's going to give a lot more weight to string theory. Of course, I think there are a lot more challenges. We have to look at how to compactify the string theory, but that could be, in my opinion, maybe an indirect way to experimentally probe string theory, maybe. Yeah.
Okay, thank you so much, and thank you for all the insightful questions. I just want to thank the rest of the NSBP team and the Student Council and the KITP team, and of course, Morgane, for this amazing talk and for being our invited speaker today.
Thank you for having me again.